As we have seen, alkynes such as acetylene are very useful both in industrial applications such as welding with our acetylene torches, as well as in our organic lab where we can perform alkylation reactions to expand those alkynes into larger molecules. Now, of course, the question is, where do we get these alkynes, right? If we're going to be burning this up like crazy in our welding, we need to have a good source for it. So we're going to look at a couple different sources for these alkynes. The first source is calcium carbide. So calcium carbide can be produced from a combination of lime and coke, basically carbon and calcium oxide compounds. This is done in an industrial setting at high heat, and what it gives us is this combination of calcium with our carbide. Carbon's triple bonded together, so this is a -2 anion, and we have our +2 cation bound together in this ionic compound. And when we combine that with water, it can react and produce our acetylene as well as our calcium hydroxide. This calcium carbide reaction can be used to create large quantities of acetylene. This is how acetylene is generally produced in industrial settings. And of course, that acetylene can also be used to make a variety of other alkynes, as we've seen with our alkylation reaction. So this is a very useful way to produce large amounts of acetylene. Now, we do have several other approaches that we can use as well, and these are a little bit more flexible. They can potentially be used for other alkynes instead of just acetylene. So the first is dehydrogenation. Now, dehydrogenation, of course, we talked about briefly with alkenes. It's the reverse of our hydrogenation reaction. One of the things that we mentioned there is that it requires a high degree of heat because you're actually reversing this exothermic hydrogenation process. Right? So it's generally only done in industrial settings and requires just a lot of energy to make this happen. But if we take an alkene, such as ethene, we can react it with excess heat, and we can force those hydrogens to break off from our carbons in order to make, again, acetylene, and in this case, hydrogen gas. So again, it's somewhat difficult. It requires a high degree of heat. It's usually only done in industrial settings, but again, it can allow us to produce acetylene in relatively large quantities. You could potentially try to produce other alkynes here as well, but the issue that you would have then is that you might have dehydrogenation occurring at other points in your molecule besides just where you want to form your alkyne. Our third main method for forming alkynes is double elimination. Now remember, of course, if we have halogens, we can eliminate hydrogens from our adjacent site. We refer to this as beta elimination. So we can bring in a strong base, and we can pull off our hydrogen while kicking off our halogen in order to create an alkene. So this is the standard elimination that we've seen in our previous alkene reactions. Now, of course, you should notice that we have two halogens in our starting molecule, and of course, one halogen left over on our initial alkene product. So we refer to this as a dihalide. And in this case, since they're both attached to the same carbon at the end of our molecule, we refer to this as a geminal dihalide. So geminal just refers to when we have two of our function groups attached to the same carbon there. So since we have this second halogen here, we can do a double elimination if we have sufficient base, where we can actually repeat our elimination reaction in order to produce an alkyne. Right, so we eliminate again, and we go to our alkyne product. Now in this particular reaction, you should notice that our product is a terminal alkyne. We were using a very strong base in order to deprotonate and create our elimination reaction. So we actually also have the possibility here of our base reacting with our alkyne product. So this would produce that alkyne carbanion that we've seen in our previous videos. So often we'll then add water in an extra step, and water will protonate this in order to form our alkyne product. Now you might ask, why don't we just use an internal dihalide so that we don't have to worry about creating that terminal alkyne that's then going to react. But the problem with an internal dihalide is that you'll have potential regioselectivity issues where you could be forming double bonds on either side of your halogen. Right? So for example, if we add another carbon in here, so we have another carbon there, so now our bromines are at the second carbon instead of the first carbon. Once we get to this point where we've formed one of our double bonds, right, we also have the possibility of forming double bonds over here by eliminating these hydrogens as well. So you potentially have two different reactive sites, and so you'll have other alkene products competing with your desired alkyne product. So generally we only like to use general dihalides for terminal alkynes. Now we can also perform this sort of double elimination with a vicinal dihalide. So vicinal dihalide is when we have our two halogens on adjacent carbons. And again, we'll have hydrogens here on both of these carbons. And we can eliminate these hydrogens by adding base. So we would add 3 units of our base. We make sure to add excess base so that we can eliminate both of our halogens, as well as then when we react with our alkyne product, we'll have excess base for that as well. And then we'll add water to protonate our alkyne to get our final alkyne product. So in this case, we would eliminate both of these chlorines, and we'd be using our hydrogens to make our double bond. Kick off 2 hydrogens from either side, kick off our chlorines, and make that triple bond. Now what we see here with our double elimination reaction is we have a more flexible way to make a variety of different alkynes. Right? We can have any kind of carbon-based structure as long as we have those 2 halogens found either right next to each other or on the same carbon. We can add strong bases, eliminate them to create our alkyne. We are still generally creating terminal alkynes because we don't want to deal with potentially multiple double bonds forming in the middle of our carbon chain if we have the internal dihalide. But we can have any kind of carbon-based chain over here, just as long as we have that attached here with our 2 halogens at the end, we can still eliminate those and create that alkyne. Again, of course, this alkyne can be expanded using our alkylation reaction, so we could essentially use this to create any alkyne that we want. So this is one of the most flexible ways to make alkynes in the lab. It allows us to make a wide range of different alkyne-containing compounds.